sound moves in the form of waves in the air. When those waves hit the diaphragm of a microphone, the diaphragm vibrates in a way that is identical or analogous to those waves. If you feed a steady signal to that microphone, its output will be modified to exactly or almost exactly reflect the form of those waves. If you amplify that signal from the microphone and send it to a speaker, the speaker's cone will move in agreement with those waveforms, and it will reproduce the waves that you sent to the microphone in the first place, only louder. An analog signal will not mean much to a computer, so we use audio interfaces commonly known as sound cards to convert analog signals to binary numbers, that's ones and zeros, that computers can understand and process. When you plug a microphone to your audio interface, the analog to digital converter in it will measure or sample the signal at certain intervals. This interval is called sampling rate or sampling frequency. The most common sampling rate used in home studios is 44.1 kHz. This means that your audio interface will sample your analog signal 44,100 times every second. It will then convert each of these measurements or samples into binary numbers and send them to your computer. Your computer will store these samples on a hard drive, and when you play this audio file, it will send them back to your audio interface. The digital to analog converter in your interface will convert these numbers to decimal numbers, and it will try to reconstruct the original waveform as accurately as possible. And this was an introduction to digital audio in almost 60 seconds. Now let's look more carefully at what happens during conversion to binary numbers. If you were using a hypothetical 4-bit system, your audio interface would convert the amplitude of each sample into a 4-bit number. That's a 4-digit number, and each of its digits can either be 1 or 0. That gives our system a total of 16 possibilities. In other words, in a hypothetical 4-bit system, the amplitude of a sample can only be expressed on a scale of 1 to 16. In a 4-bit system, the y-axis of this graph can only be divided into 16 steps. Of course, that's not enough to give us sufficient resolution to reconstruct the original signal with fidelity, so we use higher bit rates or bit depths. The standard bit rate used in most home studios and required by music platforms such as Spotify is 16. Working in a 16-bit environment gives us a bit more than 65,000 possibilities. In other words, our resolution for the y-axis of this graph is around 65,000. That's not bad, but most professional studios today use 32-bit floating point, which gives us a resolution of, well, I don't know how to read this number. You have 38 zeros after 10. That gives us more than enough resolution to accurately reproduce the original audio signal. But there's one problem. No matter how big this number is, you still cannot go one step above it. And that's the main issue with digital audio. If I try to turn up the volume and force this waveform to go above the highest possible number, the system will not have any way of expressing those numbers and will keep returning the maximum value. So the waveform will be clipped at the points where it tries to go above this value. You will remember that we talked about clipping in the third video on decibels. This is where that comes from. In digital audio, no matter how high your bit rate, you cannot go even one step above the maximum value, or you will cause clipping, and that will sound nasty. Now you know why the VU meters turn red when you have clipping. We will talk about how to take care of clipping in the practice section of this course. Congratulations! You have completed the section on the science behind mixing. You now have a much better understanding of the most important terms and concepts that we will use in this course, and you will use throughout your musical journey. Up next, we have a quiz on topics covered in this section. Go ahead and take that quiz to see how well you have absorbed this information. Then I'll see you in the next section of this course, where we will talk about room acoustics, why it matters, and what you can do about it.